Video recording is on. Good evening, everybody, or all four of you. Maybe it'll be more in a few minutes. Oh, that's a bit of a problem. There's nothing there to link to. I hate it when that happens. Well, let's get this web link up and running. All right, we'll start all that over again. Welcome to another installment of Water Systems Design. Today's topic is actually pretty simple. We're going to look at some design guidance documents from some various jurisdictions. And mostly what we'll see is a certain kind of commonality, perhaps not in the actual numerical values, but in the layout and the kind of information that's required from a designer as well as available to a designer. So on the Blackboard, the link is active and it goes to wastewater design collection criteria and it says review of design criteria. If we go in the notes, if we take lesson notes, it's currently blank. What's important are these various web links. And I think I'll start with wastewater systems design. This is on our class server, and it is an excerpt from the Land Development Handbook. I've referred to different chapters in other parts of the course. And this has a pretty good, thorough yet simplified discussion of wastewater collection in the context of civil engineering design. It has an overview, presents a brief history of its importance, has some definition of different terms, what a sewer is, sewage, main and trunk sewers, interceptors, outfalls combined, maintenance holes, infiltration and inflow, which we discussed a little bit at the end of last meeting. In this case, infiltration is groundwater that enters the system and it discusses the different ways that it can happen. And inflow is surface water that directly enters the system, and the principal sources are through maintenance shafts and unauthorized connections. It also has some other definitions. Exfiltration is sewage getting out of the sewer. Sewerage, the term in general, refers to all the wastewater infrastructure. A pump station and force main refers to the components of a system where we have to add energy to keep it moving down its merry way. Then this chapter discusses characteristics of sewage itself, illustrating that the two most important quality features are biochemical oxygen demand and suspended solids concentration, and you've probably measured both in the environmental engineering course. They've been around a while and they're still in use, and they're pretty good metrics of the performance of a system. And then it gets into quantity, or how much. And generally, the methods of estimating sewage flow are either based on the development density or on a per connection count, like we saw last time. And it says most states and many utilities have established minimum design standards for sewers, and we, the engineer, have to be responsible for those, familiar with those for the areas where they'll be installed. And we'll look at a few of them. This chapter claims it's taking requirements from Fairfax County, Virginia. The variation in fluid flow is discussed, and it shows a peak factor equation that is available, and Texas has its own set of such equations where P is the population in thousands, and this peaking factor is the number that's multiplied by average flows to estimate peak flow for designed discharges. And then the sewer is designed to accommodate that peak flow. Here it makes the dramatic statement that sewage is considered to have the same hydraulic characteristics as water. And that pretty much means that we can skip ahead because we by now know how to deal with the hydraulics of water. Here's an example of a peak flow multiplier based on average flow. And again, for less than and greater than 1 million gallons per day. It has a graphical presentation of an open sewer, not open to the atmosphere, but with a free surface. So this is a gravity sewer. This is how we want them to behave. And then here is a pressurized system, which normally is not the approach that we're taking with gravity sewers, although in some instances this may be appropriate, but it's uncommon even in the US. The chapter goes on to present our favorite chart that we've seen before. We used it in stormwater exclusively, and the chart demonstrates the little bit of excess capacity that's conferred by use of circular pipes. In the days before the invention of the gonculator, we used these nomograph tables to perform the calculations, but now that would be replaced by a calculator or a web page. And it has an example problem. And then the remainder of the chapter spends a great deal of time and space on the structural aspects of buried pipes. And we've kind of glossed over it this entire semester. But in addition to carrying water, the buried pipes also have to carry, damn it, that really hurt. They also have to support effective stresses, the overburden pressure conferred by the surrounding soil, as well as any loads at the surface. So if a pipe is buried underneath transportation infrastructure, there'll be loads imparted on it by the weight of the soil above it, plus the vehicular traffic on top of that. And there's a fairly extensive procedure on how trenching is done and backfill is done to accommodate the different kinds of loads in different characteristics. So for example, in this picture, and let's see if they have, let's see, loose backfill. I was kind of hoping for an example of cement stabilized sand, which is the common approach that's used in the Houston area. And we'll be looking at their design manual shortly. Then there's the necessary stress calculations and equations that associate depth to diameter and different soil stresses. And that's pretty much the remainder of the chapter. And then it goes into detailed design of maintenance shafts. And I want to call your attention to this part of the figure here where the cursor is circling around. And we're looking down a sewer pipe. That's what this round part is. And then we see in this vault box, there are these portions of concrete that are built up pretty much to the spring line of the pipe. And this is called benching. This concrete here is benching. It serves two roles. Its main hydraulic role is to prevent these corners from filling up with sewage solids, but the other role is as you climb down this ladder, it gives you a place to stand rather than standing in the open sewage. Because if that wasn't the case, that whole vault would be filled to the bottom with raw sewage, and you'd have to step in it to perform maintenance. So the benching alleviates the need for having to wade around in sewage. Now you still put on proper, basically waders and really good rubber boots, because stepping in sewage is no fun ever. And then this detail shows a drop manhole. So the way they're designed is flow is supposed to come this way and drop down this pipe. There's overflow provided. You don't want to physically enter this sewer when this upper pipe is so active that there's overflow coming from the high one. Here's another version of it where it's capped off, but it would still be a provision for excess flows to be able to get in the sewer if these pipes were damaged or blocked. And then it has some discussions on manhole cover rims and various designs. So this is actually a really good read. Everything you need to know about sanitary sewers condensed into 35 pages. But no specific design guidelines. If we move to the Texas Administrative Code, which I was quoting from last time, we can see how those various requirements are to be implemented in Texas. And so this is coming from subchapter C, paragraph 217.51 to 217.70. And what these design guidelines are is they have information on pipe design, and then on what basis the design has to be made, and then the materials. It states an explicit design life of 50 years. And the pipe selection is based on the listed characteristics. Then it has a section on how to connect pipes, and the various connection methods are listed. Reinforced concrete is usually done with gaskets, and most of the remainder are either done with compression fittings or welded of some kind. So PVC and HDPE can be solvent welded. HDPE is usually heat fused. PVC is solvent welded, and although it's rare, a steel pipe could just be stick welded. It lists the technical specifications that have to be adhered to for the different parts of the sewage pipe system. And the next section discusses separation distances between sewage and water supply pipes. And there's a list of criteria that are supposed to be met. And if it can't be met by separation, then we upscale the material choice. And discuss what to do in active geologic faults. And then next we have a capacity analysis. So this is to make sure that we make the system big enough. We have a prescribed minimum diameter for gravity pipe in Texas of 6 inches. Again, big enough to accommodate a beer can or a small stuffed animal. Stormwater connections are prohibited. And then there's the structural analysis aspects. So we're seeing much of the content of the Land Development Handbook chapter being reiterated here, or pre-iterated, I suppose. Then there's a set of equations dealing with structural aspects of piping, and somewhere in here it says a minimum burial depth. And now we're moving into the hydraulics. So minimum and maximum pipe slopes are prescribed. And these values are chosen, strangely enough, based on pipe diameter. I'm sure there's a historical reason for that. The minimum slope is enough slope to guarantee that the sewage will flow in the pipe at least 2 feet per second and less than 10 feet per second. So the min-max are selected between these ranges in order to satisfy that requirement stated there. The velocity decision is made to convey solids to the outfall. Manning's equation is repeated for us. A discussion on pipe alignments, a discussion on bends, and then a section on inverted siphons, which are not used a lot, but they are a useful tool when you have to go underneath a stream. And there are important design requirements. These are actually not that hard to design and build. This listing of requirements is mostly so that after it's been built, it can be maintained. Because one of the challenges of an inverted siphon is once it's built and in place, you can't very easily go down and fix broken parts. So it needs to kind of be done right the first time. And then there's a portion of inverted siphons that never dry out. So there's a fair amount of engineering and construction art involved with the inverted siphon. But it's an effective way to cross a river without having pipes up in the air, hitting people in the head as they go kayaking down the river, and collecting debris so that in a high flood situation, the river becomes a lake. And then it has specific criteria for different kinds of pipe, discusses soil compaction and backfill. And the state code is pretty simple on that. It simply says the backfill must not compromise the structural integrity of a pipe. That's an awful lot of freedom and is potentially a location where the contractor might not really care. Just put the pipe in the ground, fill it with dirt, move on, get paid. No critique of them on that. This is every bit as important as the hydraulic part of pipe design, because in many instances, once the pipes are placed, we build infrastructure on top of them. We can't very easily go back down and repair them. So again, it needs to be done as well as you can the first time. The Texas Code has a reasonably elaborate discussion of trenching and backfill terminology, and has specific standards for different pieces of that. Manhole spacing required at the state level is shown in table C2 here. It's slightly different in the Houston document. The spacing is closer in Houston, which is fine. Discuss manhole covers, inverts, and a bench has to be provided. The invert can be filleted to prevent solids from being deposited. If the manhole enters the wastewater collection system greater than 2 feet above the invert, and if it's more than 2 feet, it's required to have a drop pipe. And so they made the 2-foot requirement not necessarily for hydraulic reasons, although I'm sure there's some, but literally if you're in the maintenance hole and sewage is coming in greater than 2 feet off the bottom, it's going to hit too high on your body and fill up your waders with sewage. And you'll have the ultimate example of poopy diapers in that case. So this is mainly a requirement to protect the maintenance staff, the people that have to go down and maintain the sewer system. Next, it discusses venting for manholes that are a long distance apart, because in some places that has to be the case, and cleanouts, and then a whole section on trenchless installation. And as we're moving down here, I think there is a section on burial depth. It's only if we stumble onto it, because I'm not going to be able to find it if I'm looking through it quickly. But I believe in Texas, the minimum burial depth is 3 feet. And less than that, there's a insufficient soil to actually help distribute the surface pressures and protect the pipe itself. And as we're moving down here, we're getting close to the end. It discusses force mains, has a material requirement that it has to be able to handle the forces involved. And that has to be at least 150 psi materials. And it has to be identified with the appropriate specification number and quality control number from either ASTM, ANSI, or American Water Works Association. And the life of the material has to equal or exceed that of the lift station and be suitable for the material being pumped. The more on force mains, here's interesting portion, is on the force main, buried along with the force main is a detector tape that's labeled with pressurized wastewater. So it kind of seems dumb to put a pipe in the ground, put labels on it, and then bury it. But that overkill in terms of labeling is to protect future workers. If they dig into that and they come across the detector tape, they know that that pipe contains pressurized wastewater, and they don't want to break it. And we can laugh, in this class and say how overly prescriptive these design guidelines are, but they've worked quite effectively for 150 years in protecting the public health of the citizens of the United States. And it's one of those rare occasions where it's worked for a while. This is not the time to start taking shortcuts. We need to maintain this because a wastewater getting into the drinking water could make an entire city very sick very quickly. And that'd be bad. And I believe that's all of any great interest here. But keep in mind the layout of that as we look at the City of Houston Infrastructure Design Manual. Chapter 8. Almost the same layout. It defines things, sewer lines, community sewers, stub outs, force mains. It has a list of the design requirements, in this case, what has to be provided to the city for approval. And by far the most important thing is the receipt for the wastewater impact fee, because that helps pay for things. And then it has specific requirements of what information is to be included on the drawing. Now, most design engineers hit most of these items anyway. They're likely to get them anyway. This is more of a reminder checklist to check your drawings before you submit them on the various aspects of what has to be included on the drawings. It discusses what the plan view has to show, what the elevation view has to show. Excuse me. And in the case of a subdivision, like a sewer drawing on a plat map, it has to show the location by station of all the service leads and service stacks. So just showing the houses is insufficient. You actually have to show the connections. Then it provides guidance on what these service leads are and how they're to be treated. And if they're longer than 50 feet, then they are treated as a public sewer and are to start and end at a manhole. And then if they carry more than 5,000 gallons per day, there's some additional requirements. And the city of Houston has a minimum grade and a maximum minimum grade for 6-inch and 8-inch diameter pipes. Somewhere else in this document are maximum slopes. And the burial depth is 3 feet below the surface of the natural ground without side ditches. And if they're laid in a curb and gutter street in the right of way, it's 4 feet from the top of the pipe to the top of the curb. So that's basically 3.5 feet. And then sewers laid within a street right of way with crowned roads and side ditches have a minimum cover of 6 feet from the average ground line at the adjacent street to the top of the pipe. So the burial depths are explicitly prescribed in this design manual. Minimum maximum slopes based on pipe diameter are provided in table 8.1. And see, we got burial depth, we got slope. And I think the flow requirements are discussed elsewhere. And in the case, Houston happens to have guided rapid transit, which is a fancy name for choo-choo train. If the sanitary lines are crossing under the choo-choo train tracks, they have to be steel cased with a minimum diameter of 10 inches. And so to cross the railroad tracks, because railroads are kind of difficult to take out of the way if you have to repair the sewers, you're basically building that portion of the sewer is bomb-proof. They're quite over-designed in those locations so as to reduce or eliminate the need to ever go back at them again. The analysis for Houston are design flows at completion, a design for any treatment plant, and then calculations assuming that at the outfall, a 25-year storm flow depth is contained in the receiving stream. So that's to create or to assess your design under some backwater conditions to help you determine locations where the sewer may be insufficient and it might back up. Again, the drawing includes layout sheet with contours, plan profile, detail sheet. And so the contour mapping we did earlier on was not entirely made by me just to make your lives miserable. In fact, none of it was. Okay, before we go to Seattle and take a look at their criteria, let's look at a master's thesis on the design of wastewater collection system for a location in Brazil. And this was for a master's of engineering and civil environmental engineering at MIT, circa 2003. I don't think I've ever met this person, but maybe. I know this guy, Harleman, quite well. And in this thesis, the reason I selected it, this is actually a pretty good go-by of the kinds of things that one would do if they were a prudent engineer doing the conceptual design aspect for a particular location. So she hit all the big pieces. So this is actually a really good design document. So like all engineering reports, introduction, background, and then the methods that are applied, then a set of estimates, and finally a recommendation. And what I like about this is a discussion on different kinds of wastewater collection systems. We'll get to those shortly. So first, an overview map. This is down in Brazil, where they make Brazilian stuff. And Parate is a small coastal city in the state of Rio de Janeiro, and known for gold, coffee, and whatever they make now, which is probably oil. And in this location, there's a desire to take the older part of that city and provide effective sanitary sewage, which currently it did not have at the time of this report. And roughly by 1985, only about 83% of the urban areas in the nation had effective sewerage, and the percentage of people connected to sewerage is 35% of the population. That's not very good. The United States is far better than that. We're a wealthier country indeed, but there's no really good reason why this is so. So this design will certainly help this community. And then a brief overview of the data. Here's more importantly, this is the old area of interest. I think right here is an airport, and the study zone is actually this zone 1. And the proposed locations of the sewage are a treatment plant, I think over here, and there's another one over here. And we're going to look at an aerial image in a second, and we'll see some interesting things in that aerial image. And so the methodology of this was to obviously make a field visit and then start some mapping and go through some different potential wastewater systems. So what I've been talking about the last 2 class meetings are what would be classified as a conventional gravity sewer. So we're transporting wastewater by gravity flow. We're using elevation changes to provide the energy to do that. And where that can't be done, we put in a lift station and we lift the wastewater and again let it go on its gravity merry way. These systems can handle solids as long as we maintain an adequate minimum velocity, and that in turn helps reduce the production of sulfides and methanes. And the self-cleaning slope says it can require deep excavations. So in the US, there's a limit on that. I think it's 20 or 24 feet is the maximum excavation depth for sewage or for a sewer. And then you're getting into some pretty exotic work, or lift stations along the way. So to maintain self-cleaning, we often have to put lift stations in anyway. There are alternatives to conventional sewers, and we're going to look at one of them, which is called a pressure sewer. So a pressure sewer takes sewage, and then it goes through a macerator pump, and that converts the sewage into a slurry, if you will, kind of like your garbage disposal, but on steroids. and that slurry is forced through a one-way valve into the sewer system. The attractiveness of the pressure system is smaller diameter pipes can be used. There's no concern about infiltration because if there's any faults in it, the sewage is going to leak out, not in. The pipes don't have to be buried very deep, and you don't have to put much emphasis on slopes. They can follow the topographic surface because we're literally just pumping sewage to the treatment plant. These have a higher maintenance requirement compared to a gravity system, but they're attractive in some sense because they're certainly easier to design. If you're going to go with a pressure sewer, your design challenge is reduced in some sense because you're not worried about slopes anymore. You just connect the pipe from the tailpipe end of the colon to the treatment plant and try to avoid intersections and houses and stuff. And it still's underground, but it doesn't have to be laid on a precise slope. Similar to a pressure sewer is something called a vacuum sewer. And a vacuum sewer temporarily stores wastewater in a holding tank. And when there's enough waste, then the holding tank is opened and the sewage is sucked into the system. So these are not high vacuum. They're just maybe a half to 2/3 of an atmosphere below ambient, and it's basically sucking the material into a network of collection piping. Vacuum sewer systems can be more elaborate in that they actually can use blowers and they can move a lot of air, so you can have an air slurry mixture, and they can be pretty effective. You've seen vacuum sewer systems used at the bank when you put your money into that little cylinder and then you stick it in the thing and press the button and whoosh, it's whisked away. And you'll notice if you've ever done motor banking that putting money in, it goes away pretty easy, but getting money out, it takes a while because I guess the solids are bigger. No, just kidding. It's the same speed either direction. But that is a extreme analog to a vacuum sewer system. Another example of a vacuum sewer system is the Hyperloop. That's the demo's being built in Las Vegas, and there's the idea of Hyperloop vacuum systems for transporting the worst kind of sewage, the mighty human being, between San Francisco and Los Angeles in an hour or so, which, having lived there one time in my life, that's pretty quick. The best time I ever made from San Francisco to the part of LA I lived in was 5.5 hours, and that was much of that 5.5 hours was spent well above 80 miles an hour along an interstate that was heavily patrolled by the highway patrol. And so it was kind of luck that I was able to make that entire drive without getting a speeding ticket. I'm thankful for that. But the Hyperloop would be a great contribution to commerce between those two cities. So how do we get out Hyperloops? The physics of them is pretty much the same as a vacuum sewer. And then she categorized a fourth category called small diameter gravity sewers. This is really just a special case of gravity sewers. And then looking at these different types of sewers, performed a cost analysis in dollars per household. And the costs are kind of what one might expect. A gravity sewer is the least expensive. A vacuum sewer is, in this chart, about double the gravity sewer, and a pressure sewer is almost 3 times as much. That's cost per household. Now at the sewer mains, the dollars per meter of sewer main decreases proportionately to the system type. There is some capital expenses associated with lift stations for gravity sewers, the required pumping station for a vacuum sewer. And here the chart claims that there is no cost for pumping for a pressure sewer. That is deceptive because a pressure sewer system, there's a pump at every house. And so the pump station costs that normally would appear over here and be paid collectively are really hidden in this $7,000 per household number. Going through the analysis, the end result is probably what you expect. The operation and maintenance costs are worked into the pressure system. There's a few site examples that are listed. The cost based on population density, and lo and behold, ultimately what's concluded is that for this location, a gravity sewer is probably the most cost effective for this small portion of a town in Brazil. This is an interesting chart that shows that as the population density increases, the cost per capita of any type of system decreases, and at high density, 100 people per hectare, which would be 40 people per acre. That would be like, let's see, 10 houses per acre in a city, which would be pretty high density because most of our lots are a sixth to a fifth of an acre. The gravity sewer is actually quite cost effective, the dry gravity. Wet gravity is kind of what we think of as a pressure sewer. So part of the reason why gravity sewers have been attractive in the United States and globally is they are the most economical in cost per person served. They're also historically easiest to build because the other ones hadn't been invented yet. So the decisions in this particular design were expandability, adaptability, and simplicity, which is not to be understated. The simplicity is important because these things need to work for 50 or 60 years. It can't be overly complex because if it is, the chances of it failing before the end of its service life are quite high. Vacuum systems take a full-time system operator, and a single vacuum leak can render the whole system inoperable. Pressure systems, similar requirements. So ultimately, in this particular study, the choice was a gravity system. So once we've decided what system, the next is to start to design it. So here is an aerial view. So there's the airport I was pointing out earlier. And here's the two potential terminal locations. So one of them would go from the historical center, and you would convey sewage probably across the airport right away. It looks like there's an inlet right here. So you would probably want to go along that street and get over to this location. The other location, location number one, isn't nearly as far in distance, but we have this small little nuisance of this canal in the way. And so the sewage would either have to go over it, under it, or I guess you could take the chicken approach and just discharge straight into the water, problem solved. And the the nearby site is undesirable because it's close to a beach. So here you have a beach where people try out their various beach-going toys and clothing. So the ultimate selected one was location 2, which actually makes good engineering sense despite the extra distance, because we can stay out of the water the entire sewer run. to get to it. And putting a sewer line across the end of the airport, that's probably pretty feasible. You only have to stop air traffic for the hours during trenching. Any plane that lands in the trench deserves to be ripped out of the sky, and then you would be done and on about your way. So in this design, the designer used a GIS system, and I think it's called HydroCAD. What was the integrated? There was the integrated software tool. Hasted, I think it's called Hasted Sewer CAD. So what it is it's a software that interacts with a GIS system, and on one end and on the other side, it interacts with a hydraulic model. Most likely SWIM. Actually, I know it's SWIM. And so in this study, there were a couple of potential designs. One was to take the sewer flows, run them all down to this main street, and then run that off to the plant. And that, at initial glance, isn't a terrible design. The other one is to run a main trunk line kind of down the middle of the area and basically reduce the lateral run lengths considerably. Ultimately, I think design 2 is what gets selected, and then goes through the various design factors. Average daily flow, in this case based on population, loading, sewage catchment areas. This is almost the same kind of tabulation that you do for stormwater, only it's sewage water. Peak flow, infiltration, sewer materials, depth of cover. In this particular study, the depth of sewers is 0.4 of a meter below the ground surface, which would be less than 2 feet. That's kind of shallow by our standards. And it says in Brazil, the minimum cover is 0.6 of a meter. But because there is no vehicular traffic, they decided that reducing the burial depth was acceptable, because the only forces the pipes have to resist are the forces of people walking on them. There's no vehicular forces. So the shallow burial depth makes sense. Depth of excavation and the velocity requirement. Gravity, that's cute. 0.6 meters per second flow velocity, and then there's a set of recommended slopes based on diameters. So this was the starting point. Ultimately, the model used is called SewerCAD, which actually implements a type of SWIM model. And I want to take you to this drawing here, because everything featured on that drawing we've examined in SWIM. So each of these little circles labeled MH3, MH2 represents what? A node, a link, or a pump? Waiting for it? Waiting for someone to say node. Each of the parallel lines is representing a conduit. When we get to this end, we have a storage unit, goes into a pump, and the pump discharges through a force main to an outfall. So this is totally interfaced to a SWIM model. And so there's the gravity sewer network, and then here's the profile plot. And you'll notice initially, just like a profile plot in SWIM, the only thing that's a little bit disturbing to the eyes are these offsets not matching the crowns. There's a set of pipe lengths and the various flow rates. Cost estimate, bit over $1 million, 150,000 a year to operate. That's not bad. And then the discussion and analysis. And finally, some other analysis, looking at the effect of peaking factor on velocity. Even at the highest anticipated flow rates, velocities are still less than 0.8 of a meter per second, so less than 4 feet per second, 8 times 3, and above 2. So we're pretty much in the solid transport range in this entire envelope of possibilities. And then the total flow versus peaking factor and infiltration rate versus total flow were performed to see how sensitive the system was to those. And we actually can get an idea of the impact of Manning's N in this system. It has some effect on velocity, but not as much as one would think over these ranges of Manning's N. And going from 0.01 to 0.013 that's pretty much all the same number. That's the reason those are flat lines. And there's one of the important observations. Under the design system operation, there's no flooding. And the recommendations are listed here. And I want to get to the conclusions, which is nothing unusual. They concluded that gravity system could serve the historical center, and they actually provided a conceptual design. And the important part was right here. So this was the initial profile that I critiqued as not having the sewer crowns mating up correctly. This one didn't either, but I did notice that as you moved further into the profile studies, they did indeed have them designed the way one would want to. We want these pipes to join at the top, and what that leaves is extra capacity to carry sewage and solids on downstream. And I'll just get to the end of that. There's more profiles. And so this is a good example of a fairly thorough sewer design study for that particular area. All right, let's go to Seattle real quickly, and we will be done. So the Seattle design manual's pretty cool. It's really nicely organized. And like the other ones, it starts out with definitions and abbreviations. It tells what needs to be on the design sheet. And then they go into a storm drain design and sanitary sewers design. So the somewhat obvious mismatch of storm and sanitary in the same chapter actually makes sense for Seattle because they historically have a combined sewer system. And so it makes sense that the two design procedures would be in the same chapter. Let's go look at sanitary sewer design. It discusses the point of a design, the capacity analysis. So they use population-based, system layout, sewer mains are a burial depth of 12 feet, and somewhere later on it's going to discuss what the laterals or the service mains are. Sewer pipe minimum 8 inches. Sewer pipe must be sloped so that when they're full, the velocity is bigger than 3 feet per second. If any slopes are less than 0.5%, they need Seattle Public Utilities approval. The pipe materials, clay pipe is specified. That is unusual. I haven't seen that in quite a while. So maybe Seattle's the last holdout for vitrified clay pipe. The statements here are true. Clay pipe is remarkably resistant to wastewater. But it has installation challenges. It has to be done by high-skilled installers. The public utilities prefers ductile iron pipe for force mains. It states that sanitary sewers have a minimum cover of 12 feet. If it's less than 12 feet, they need approval. Connections and tie-in requirements are explicitly stated. Cleanouts, there's design drawings or specifications that you can use. They use the word maintenance hole, what we know as manhole, but it's actually very clever that they were able to keep the initials and stay somewhat politically sensitive. So if they go up to 40 feet deep, there's one set of specifications. If you go greater than 40 feet deep, there's a different set. Greater than 40 feet deep, you have some substantial structural challenges, which is why they would separate the two. Discusses where they have to be, every change in grade, every change in pipe size, every change in pipe alignment. Always at intersections, always on the upstream end of each line that has an 8-inch diameter or greater pipe. It has some useful drawings and a section on combined sewers and some more useful drawings, and then various construction aspects. So that's the Seattle one. Contains essentially the same type of information that was in the Houston Infrastructure Design Manual. And lastly, a parting shot, and then we'll almost be done. The Seattle book design manual has a whole chapter on drainage and wastewater system modeling. It discusses what a modeling plan is, quality assurance milestones, some various information, how to archive and maintain data. That's actually pretty smart. And then how to actually build a particular model, model testing, precipitation, flow monitoring, calibration and validation, and then an uncertainty assessment. The preferred software is SWIM. So you're all being well trained for moving to Seattle and working there. They're not the only place in the country that uses that. And they stipulate that when SWIM cannot be used, you can consider some other ones. HEC-RAS, which would be really stupid because there's nothing HEC-RAS can do that SWIM can't. Mike Urban or Mouse could be used. Mike Urban is an enhanced surface-subsurface drainage model. Ironically, it uses the SWIM computation engine. So again, I find it hard to believe that you can find a situation where this will meet your needs and this one won't. Mike Urban might be easier to use from an end user point of view. So that's a good thing to have in your toolbox, that there's at least this one set of criterion. Thought I'd get my cat to say hi to you. Say hi to everybody. Oh, you don't like that, do you? The last thing to look at is the American Water Works Association wastewater design tools. And so they have a whole section on wastewater collection system and a lot of technical resources. There's different guidance manuals, and these are available in exchange for money. $116 for a manual on valves. That seems like a lot of money to you and me because we don't deal with valves very much, but if you're in the business, That's probably pretty cheap. And again, if you notice, the Texas code explicitly states AWWA standards and specifications are acceptable to the state of Texas. So that would be worth the $118 to be able to design and build your project in Texas. And that pretty much concludes today's lesson. Thank you for your attention. Have a good evening, and we will meet again on Tuesday. I hope that I will get some I hope I'll get a couple of homework assignments posted, but over the weekend, and we're almost to the end, so that's good. It's been a pretty good semester. Again, thank you all for your attention. If there's no questions, I'm going to go ahead and stop the presentation, and I will see you next week. Have a great weekend, everybody.